Okay, excellent. And then I'm also going to turn my video on just because I think it's easier if you guys can see me talk. There we go. So video. All right, excellent. There we go. All right, so you can see me and you can see my screen. Is that correct?
We can see your screen.
Okay.
Yeah.
Excellent. Excellent. Okay. Cool. Yeah, so as I was introduced, I'm Dr. Josh Day. If you want to follow along, actually, I haven't pushed my slides yet. But afterwards, if you visit this GitHub link, so github.com/joshday/talks is where I put all of my public talks. So there's a folder in there called 2021, and in there is streaming data webinar. And so there are a number of Pluto notebooks that I'll be going over. And if I haven't pushed all of my most recent updates, I will push them immediately after the talk. So all the materials that I go over today will be in there. All right, so for what I'm going to talk about today, it's going to be very online stats heavy, which is one of my main packages that I contribute to. So we're going to talk about what OnlineStats is. We're going to use it for visualizing big data. We'll talk about working with CSVs, and then we'll work with a whole bunch of CSVs using filetrees.jl, and then we'll end with some Q&A. So if there's anything that is, super unclear during the talk, go ahead and throw that into the chat, and then I'll have Sanjeev ping me if there's a question that shows up in the chat. All right, so what is OnlineStats? So it does online updating for a wide variety of statistics models and data visualizations. And so the way that I'm using the word online here kind of predates the internet, so it has nothing to do with the web. It just means that you're updating your algorithm using one observation at a time, as opposed to having them all available at once. So in contrast to offline, online means, yeah, you're updating your whatever it is you're updating with, one thing at a time. And so then it also provides parallel computing primitives, which we'll talk about in just a second here. So the two kind of basic parts of the interface for OnlineStats are fit and merge. And so I guess one important concept is that every statistic is its own type. So looking at, one of the more basic ones, just a mean, we can see that there is a mean type. So on the right side there, it says O equals mean. I can fit that with a new observation. So if I fit it with 1, then I can see my value is 1. I can also fit that with multiple things. So if I fit it with an array of 2 and 3, OnlineStats is going to iterate through that container and add those values to the mean object. So there's the online updating aspect of it. And then we can also merge different stats together, or I guess we can merge the same stat together. So if I create a separate mean object and I update that mean object with other data, I can now merge those two means into one thing. And so that's basically the parallel computing aspect of this. So because we can alternate between fitting and merging statistics, so on this example on the bottom left there, if I have 3 means and I fit them on 3 chunks of data and merge them at the end, well, that's equivalent to only having 1 mean to begin with and fitting it on all the data sequentially. So that isn't true for every online stat, just because there are some things that are not analytically mergeable, or some things that it's required that you some approximation is made during the merging, but for many things you can do this analytically equivalent. So let's talk about the capabilities of OnlineStats. So I started working on this package back during my PhD, which would have been 2014, 2015. And I've just been incrementally adding things over time. And the whole idea was to figure out how to do basically kind of the different categories of statistics in an online matter. So we'd started with, things like means and variances and quantiles, and then moved on to more complicated stuff. And now there's just a whole lot of things in there that go over a whole lot of different kind of fields inside of statistics. So we won't have time to talk about, well, most of these things. I'm going to focus on some of the data visualization parts. But if you're curious, go check out the OnlineStats documentation. It's pretty thorough, and there's a lot of examples in there. Okay, visualizing big data. So visualization is super important. I'm pretty big into data viz. But you might come across the question of how do I plot a data set that doesn't fit into memory? So there's two like kind of common solutions to this, which is, you can buy more RAM for your own machine, or you can rent more RAM essentially with cloud computing. But neither of these are super convenient, right? So I am like giving this talk on an 8 gig RAM MacBook Air. So I would rather not buy a new computer every time I have to analyze a data set that's more than 8 gigs. Or visualize that. So we're going to take a look at examples. So there's these two types in OnlineStats called partition and index partition. And let's see. I think I have to change my sharing settings to the whole screen here. Okay. Okay, is everyone able to see the Pluto notebook I have here now?
Yeah, you can see.
Okay, excellent. Try making this a little bigger for everyone. Okay, so the partition type, that's for visualizing a univariate data stream. And so one restriction I have in OnlineStats is that everything has to use constant memory. So even if I, update my statistic with, 20 million observations, I want to have like a constant memory footprint that statistic takes up. And that's kind of the whole idea behind what I'm going to talk about here with these. I have these structs that are made for visualizing like large chunks of data. And the way that it does that is that it summarizes kind of different sections of that using an online stat. So the partition type, it creates, approximately equal sized bins of your data. And then for each one of those bins, it essentially calculates like a cross-section statistic. So here, as we add more and more observations together, once we kind of, run out of space on the right side, the bins on the left side will begin merging together. And that's the way that we use this kind of constant memory footprint. And I guess I should further explain what this plot actually is. So here I'm creating a partition, and the two statistics that I'm kind of calculating over the cross section is the mean. And so that is the blue line here. And then the extrema, which is the maximum and minimum. So when I plot the mean, it shows up as a line. When I plot the maximum and minimum, it shows up as, these kind of reddish boxes. And here I'm only looking at 10 different bins, but I could add, several hundred or 1,000 if I want kind of a better looking picture. And so one neat thing about using the extrema here is that you'll notice I'm also plotting all of the data points in black. So you notice by plotting the extrema, we know that we've captured every single data point. So while we're only getting a coarse view of what this data stream looks like, it enables us to plot it at all. Right. So if we're looking at a billion things, we would not be able to plot that. It would completely choke my computer. But if I, sequentially update a partition with a billion things, that is no problem. And I can always plot that because it has a constant memory footprint. So these visualizations I actually figured out were kind of similar to R's tab plot package. And so what tab plot is our package. So you throw in a data frame and it plots kind of a summary of each column. So if you think of what we just looked at in that animation, or this is essentially the transpose of that. And so where they're calculating summaries over kind of different sections of the data, and it looks like they're plotting, 100 different sections here. So at some point in time, I would like to implement my own version of tab plot for Julia. That's for a later day. All right, so that is for a univariate data stream, right? So we only have one variable that we're looking at. A more common thing is looking at two things together. So I have a type called index partition for bivariate data. And this is the same kind of concept as a partition. So we're calculating an online stat over these cross sections, but then those cross sections are coming over approximately equal sized bins of some reference or index variable. I haven't seen anything like this anywhere else. So as far as I know, it's unique to OnlineStats. And so here, we'll just take a look at this example here. I have an index partition. I'm telling it that the X or the index variable is a float 64. And I'm also saying that the cross sections, I want to calculate a k-hist. So there's several different histogram types in OnlineStats, and this is just one of them. But I'm essentially saying I want to calculate a histogram on the cross sections with 20 bins, and then I want 100 bins over the index variable. And so here I am just, simulating some kind of dummy data, and I'm looking at 1 million observations. And then I'm fitting this all together. And then when I plot it, yeah, we get all these different cross sections of data. So, right, so this is giving us a coarse view of it, but I think my computer would also choke if I just tried plotting these million points. At least my browser wouldn't like it. So while it only gives us a coarse view, it enables us to do it at all, like it makes it possible. And that's kind of the benefit of partition and index partition. I'm going to run back to my slides. Okay. Okay, if there's any questions on the big data viz stuff, yes, throw those into the chat and Sanjeev will ping me. All right, so let's talk about data sources for OnlineStats. So OnlineStats is designed to work with any iterator. So every type in OnlineStats, like a mean, is a subtype of OnlineStat, and it's parameterized by some variable t. And what that t is the type of a single observation. So if I try to fit a mean on anything that isn't, well, so for mean, mean is a subtype of OnlineStat t, or of OnlineStat number. So anytime I try to fit a mean on something that isn't a number, OnlineStats is going to attempt to iterate through it. And let's just take a look at that here. Let's open Julia, OnlineStats, create a mean, and let's look at the supertype of mean. So mean is a subtype of OnlineStat number, and all that means is when I try to fit it with a number, it's going to try to just update that, naturally, and I can fit whatever number I want to throw at it. So I can throw an int or a float, and it's kind of handled the same. But if I give it some sort of collection, so if I give it a vector of integers, so that is not a number, so then OnlineStats is just going to attempt to iterate through that. And so the benefit of using just, kind of generic iterators is that I can throw whatever kind of collection I want, and it's just going to work. So there is a tuple. I can throw a pair. I can do some, large multidimensional array. And all those things are just going to work out because you're just going to end up iterating, and at some point you hit a number, and then that OnlineStat gets updated. So the cool thing about working with iterators is that OnlineStats works with just about anything. And kind of showing the power of Julia here, we're going to look at csv.jl. So CSV provides some useful utilities for parsing and iterating through CSV files. And so CSV and OnlineStats don't know anything about each other, but CSV provides an iterator, and OnlineStats works with any kind of generic iterator. So they work really well together, as we'll see in a moment. All right, so let's work with some CSVs here. So for better or worse, CSV is a standard format. It's not the most space efficient format that we could come up with, but it just kind of exists everywhere because it's easy to produce. So let's take a look at how OnlineStats and CSV can work together here. And we'll go back to Pluto. So for those of you who are not familiar with Pluto, if you're familiar with Jupyter notebooks, they're similar, except they're all reactive. So if I make a single change to one of the Pluto cells, it'll update throughout the whole thing. Another difference from Jupyter is that the results show above the cell. So if I set stocks path equals to this, the line that shows up is above it. All right, so as an example, I'm using Kaggle. So they have a bunch of kind of data competitions. And one of their data sets is this huge stock market data set, which has full historical price. So the open, high, low close, and volume data for all US-based stocks and ETFs on a few of the big trading markets. And so first I'm going to set, so just the path to where all these files are. And if I can then just read that directory, I can see here So here are, 7,195 CSV files. And so every single stock has its own CSV file, and they all look approximately the same. So if we take a look at just the first one, so we're going to take a look at, we're using CSV file to read this in, just for the first file that exists there. And so the variables that we have are date, open, high, low, close, and volume. And I'm not sure what open int is, but I haven't seen any value other than 0 for any of the stocks. So we'll ignore that for now. All right, so now let's use CSV and OnlineStats together and calculate statistics directly from the CSV file. So let's take a look at Netflix here. So we're going to read this CSV file, and I'm pulling in the Netflix CSV. And then since with CSV, we can just iterate through this file object. So for here is my iterator. So I want to pull off the volume for each row in my CSV file. And then I'm going to fit it on an Extrema object from OnlineStats. And so this works pretty nicely, and it's pretty easy to use. So again, I'm not loading my data into a data frame before I do anything to it. I'm actually doing this kind of directly from this CSV file object, which is pretty cool. And so we can see that, yeah, so here is the minimum volume traded on a specific day for Netflix, and here's the maximum volume. Now let's look at a slightly more complicated example, and we're also going to use index partition again. So here I want to plot basically a course view of the history of some stock's value. So we could plot all the values together like right now, like we don't run out of memory when we do that. So we're going to have to use our imagination a little bit, but just pretend that we don't quite have the space to plot all these values. And so I'm going to create an index partition. I want it indexed by the date, and I'm going to calculate the extrema, so the minimum and maximum again, and I'm going to calculate that over 300 bins. So I'm going to read that file, and now I'm going to create this iterator. So for each row in my CSV file, I'm going to pull off the row date and the row's low value. And then I'm also going to give it the row's date and the row's high value. So this is guaranteeing that for every single date that I give it, we're capturing the entire range of prices for that given date. So then I'm going to fit this on this iterator. And you can also note that there's kind of 2 levels of iteration that are happening here. So I'm first fitting, so when I call fit on this, each element of this iterator that I'm giving it is actually 2 different things. And so I'm iterating through this for row and file one. And then I'm also iterating through kind of this like sub iterator that is getting produced by the larger iterator. So there's kind of 2 levels of iteration that are happening as observations are getting updated into this index partition. And then we can go ahead and plot that. And here we'll so there is Apple, there's Microsoft. There we go. IBM, Google. I just picked a couple random ones to plot through. And so this is running through the CSV file. And again, I'm not loading this as a data frame or anything. It's just directly from the CSV, which is kind of cool. And so again, since we're using Extrema, we're only getting, that course view of the data, but it lets us plot it at all, which is cool. Okay. So now let's talk about lazy loading. So the one problem with CSV file is that, so this actually loads the entire file into memory, which is actually something we probably want to avoid, or we're going to run into situations where we want to avoid that. It's entirely possible to have a single CSV file that's larger than your memory. So to go around that, CSV provides a rows type, and that lets you iterate through a single row at a time, and it only loads a single row. So this comes at the cost of type inference. So the only thing that we need to do in addition to, or the only thing we need to do that is different from CSV file is that we need to parse the values because they essentially all show up as strings. So here I'm going to create a rows object. And again, I'll still look at Netflix here. And then an additional keyword I'm going to add here is reuse buffer equals true. And this just means that every time I read a new row, it's going to go into the same section of memory. So it's a problem if you try to collect all the values and you're reusing the buffer, but we're not going to collect the values, so we can reuse that same memory section. Okay. So now let's do the same thing as up above. We fit this extrema and we ran through this iterator, and we can see the only difference that we're doing now is that we have to parse that row volume into an int, because it doesn't show up as an int because we've lost type inference, because we are now using CSV rows instead of CSV file. But the main benefit is that our memory footprint is just, infinitesimally smaller than it was with CSV file, which is cool. All right, so now let's do the same thing again with that plot, except now we're going to use CSV rows. And so I've created this little helper function to parse all the values into the shape that I want it. And so first we take the row date and convert that into a date. We take the low value and parse that as a float, and we take the high value and parse that as a float. And then we return those pairs of date to low and date to high. So here is our old line, which we created a CSV file instead of a file. Now we're using rows. And then now instead of this iterator, we're using our parse row utility function up above to iterate through all those things. All right, and we can see we've got the same result as up above, but we're using a much smaller memory footprint because we're not loading the whole file. We're only loading a single line at a time. Okay. Okay. So what about working with multiple CSVs? So this is a pretty common scenario. There might be some process that is generating reports on a weekly or monthly basis, or in the example that we just were working with, we had, every stock was in its own file. So it's not too hard to kind of, write your own for loops that loop over files and analyze things. But we're going to look at file trees here to help us working with multiple files at once. So one of the benefits of file trees is that it's very easy to do kind of parallel computing with it. And there's also some nice syntax for kind of getting subsets of files. And it's powered by the same tech that powers JuliaDB, which is Dagger. So Dagger is a distributed scheduler for Julia, which is pretty clever. And it works really well with file trees, as we'll see in a second. So there's basically only a few functions that we need to know with file trees. So we want to create our tree object with file tree. We want to load each file into some sort of object. Maybe that's a data frame. Map values means we want to map some function to each of those loaded things. So maybe we want to calculate a statistic from that data frame, and then we can reduce the values at the end. So maybe we want to do some sort of aggregation on all those calculations. And we'll look at an example in just a second here. So working with many CSVs. And unfortunately, I think something broke in my notebook right before I ran this, which is always the risk of running live code in a live talk. So I have a file tree as examples that works in another notebook that's open. But it appears that Pluto uses the distributed library to work with to run some of its processes, and that doesn't seem to play well with Dagger in some scenarios. So this works if you run this outside of Pluto, but I ran into a problem here, but we'll see that in a second. Okay, so file trees, yeah, so one way I tend to think of this as map reduce for file. So you want to map a function to each file. So like, read a data frame and perform a calculation, and then you reduce that as in reduce it to some single result. And so we're sticking with the same stocks data sets. And so here we're going to create our tree. And I'm just giving this file tree object this path to where all those text files are. And if we want to work with subsets, we can use glob to kind of match patterns. So if I use AAP star, it's only going to match with the file names that match with that. I can also use regular expressions to match with the things that I want, if I only want to look at a subset of things. So remember, this data set had close to 8,000 different things. I might only want to work with a few at once. So getting these subsets really easily is a pretty cool feature. One nice thing I like about file trees is that it's very easy to do things lazily. So you can kind of define a set of operations, and then you later on you can let Dagger know when to execute them, and Dagger will schedule all the things. So you can see this error below, which we'll run into in a second. All right, so here I am using file tree load. So first I'm taking a subset of my tree. So my subset is Apple, Microsoft, Netflix, and IBM. And I am, so if you're unfamiliar with Pluto, I am binding a value to this be lazy variable. So the checkbox is unchecked, so be lazy is false. And so if I set lazy equals false, then I'm going to run this function. So this do syntax is for an anonymous function. So file is the name of the argument. And so I'm saying that this anonymous function is going to read this data frame from the CSV file. I'm also going to add a new field to the data frame, which is the name of the file. And then I'm going to return the data frame at the end. And so we can see what this looks like. So I now have what looks like the same tree above, except now the values are all data frames that are associated with these files because they're all loaded. And then I'm going to use the map values function to do some sort of calculation. So here, say I just want to find out, what is the maximum price for each of these things. So I'm going to calculate the maximum for all of the high values in each data frame. And now we can see that the value is a float 64. Where this kind of got wrecked for me was this exec function. And that's what actually caused the execution to happen. And so what should happen is if it is being lazy, then all the calculations would happen inside of this exec. So you would define all these operations to happen. So if I check be lazy here, you can see that these objects change. So it's no longer a data frame that shows up here. It's a thunk. And the thunk is basically a function that hasn't executed yet. And so remember, so this do syntax is for an anonymous function. So now instead of eagerly loading all these things as data frames, I've just told file trees how I want these things loaded, but they haven't actually loaded yet. So similarly, when I call this map values function, so now this subtree underscore dfs is now kind of a lazy definition of how I want these things to be loaded. I've kind of further added more information of an additional thunk. So it's an additional function that hasn't run yet. And so you can nest a whole series of different thunks. So that basically a whole series of operations that doesn't eagerly happen. So this happens just about instantaneously because nothing has actually run yet. And then when I run exec on my lazy tree, then Dagger will do all the scheduling for me and run all of those operations. So again, this error is only showing up because I'm working inside of Pluto, which I guess doesn't work well with Dagger at the moment. And let's see, I think if I get rid of exec here, and let's not be lazy. Oh, there's a bunch of stuff that's also running. So one thing, as an example, I wanted to ask the question of, what's the average absolute difference between the low and high for all stocks? This might not be the most useful thing, but say it's some measure of volatility that we're trying to figure out. And so I'm using file trees load to load everything as an ordered dictionary. So I'm creating a dictionary and I'm pointing the file name to the mean absolute difference between the high and low. So now instead of mapping map values, I'm using reduce values to merge all these dictionaries into a single thing. And it's still running here. And again, I ran into that same issue with exec, and we'll see if this stuff actually runs here. Okay, there we go. I think that just finished. There we go. So if I'm not doing things lazily, I'm going to type this here and not run it. So this should if I'm not doing things lazily, exec should be a no op, like it shouldn't do anything because the values have already been eagerly computed. And so now when I get one of the keys of this tree, so if I look at Apple, I get, there is my mean absolute, or sorry, this is the, what was I calculating here? Oh, this was the maximum price. All right, so the maximum price that Apple was ever at was 175. All the stuff below is loading. We'll see if Netflix loads there. Okay, and similarly, so here I'm loading everything as an ordered dictionary with only a single entry. So that single entry is the file name and it points to the mean absolute difference. So when I use reduce values and I merge, it merges all those single element ordered dictionaries into one big one with all of the stocks all together. And then here I'm just picking a few to plot. All right, so we'll see a working example of lazy file trees in a little bit here. Okay, so another kind of data source that I was trying to think of was, infinitely sized data. So this is, stuff that happens in real time, whether that's, crypto or something that's only happening during the week, like New York Stock Exchange. But so here we're going to look at the TrueFX API. And so this is an API for foreign exchange rates. And yeah, so at regular increments, we're going to kind of keep hitting their API to get some data. And then we're going to update some statistics with that data and then plot it. And again, since we're using OnlineStats, there's no worry about running out of memory, even though we're looking at, some or potentially infinitely sized data set. So here is the endpoint for the TrueFX data. I'm just telling it to load as a CSV. And here is an example of, all right, so if I hit this endpoint once, this is the data that I get back. And so it is the pair of currencies, so the euro and the US dollar, the timestamp of when I accessed it, and then some other data on that exchange rate. So if I call this again, yeah, you should see the numbers all change. That's because all this data is getting updated more or less in real time. So every time I call this function, the numbers should be changing slightly. All right, so what I'm going to do here is I'm going to calculate a statistic, and here I'll just look at 3 different currencies. So the euro and USD, USD and the Japanese yen, and euro and Japanese yen. So we'll do stat equals, so we're going to group by string. So string is going to be the name of the currency pair. And then I'm going to calculate, so an expanding hist, which is just another type of histogram in OnlineStats. So we'll update that here. And just to show what's happening here. So I'm binding a variable called clock to this clock object. So once I hit start, this variable will continually refresh, and then this block of code will start running over and over. And what I'm doing here is I'm loading a data frame from that helper function for getting the TrueFX data. And then I am fitting my statistic with bid points. So I'm not too familiar with the foreign exchange markets, so I'm not completely sure what that is, but that was one of the numbers that was changing the most. So I picked that one. And then I am going to plot those histograms for each one of these currencies. All right, so I'm going to go ahead and click start here. And you can see, all right, so now every second I am hitting that endpoint for the TrueFX. I am updating that online stat, and then I am updating these plots. So I'm updating a histogram for all these different things. So I could leave this running for hours and hours, and that would give me a good idea of the distribution of, the bid points for each of these 3 exchange or currency exchanges. All right, and again, yeah, we're using OnlineStats, so we have a guarantee that there's a constant memory footprint, so we can just leave this going forever and not worry about running out of memory. All right, so my last example is more or less, my big data example. So this is a common publicly used data set, or a commonly used public data set. So the New York City releases data on their taxi trips. So they split it up between, yellow and green taxis. But so I'm looking at 2019, and it gives me, so looking at all, so there's a different CSV file for every month. All of them total is about 7.8 gigs. And I'll note that my laptop again is only 8 gigs. So it really, like, I would have a hard time loading that while, also running my operating system and, this Zoom call. If I was trying to load 7.8 gigs of memory of stuff into memory all at once. And I have a notebook. Okay, let's leave that running. All right, so let's start with an example question, which is, what is the distribution of passenger counts for each day? So I didn't give a summary of what this data looks like. 1 second here. Well, so in each of these CSV files, I'm sorry, I should have printed out just the head of one of these files. So it gives us the timestamp of when the trip happened. It gives the distance. It gives the startup, or sorry, yeah, the pickup time and the drop-off time. It gives the number of passengers, the price paid, and a couple other kind of just metadata things about these taxi trips. And so if we look at all of our files here, we see we have, one for each month. And so I'm going to create my file tree on all 12 of these things. And notice here, I am going to use lazy equals true with my file trees load function. And so again, let's think of this as a map reduce is what we're doing. And so we're getting the distribution of passenger count for each day. And so the function that we want to map onto each of these files is we're going to create a CSV rows object. So we have kind of the lightest memory footprint as possible. And then we're going to calculate a group by, which is an online stat. So I want to group by unique dates, and I want it to point to a count map, which gives us the count of every unique observation that shows up. And then here is my helper function for parsing through the rows. I have this try catch because there was some missing data in there. And then my iterator that I'm calculating here, I'm parsing the row and I'm skipping any missing values. And then I'm fitting those things together. And so, right, so this is happening lazily, not eagerly. So these are defined as thunks, and it's not actually returning the online stat yet. And then my reduce op is I'm using the merge function. So I am, with this map function, I'm creating a bunch of online stats, and then I'm going to merge them together at the end so that we get all 365 days worth of data. Okay. And so I ran this earlier and it took me about 257 seconds. If you can see on my screen, I have some like monitoring stuff on the top. So it's kind of fun to watch while this was happening because so I have 4 processors on this computer. So all of these were, close to 100%, but then my memory was staying around 33%. So my processors were working really hard, but my RAM was feeling pretty comfortable, even though I'm processing 7.8 gigs of data, and I only have 8 gigs of RAM here. So I'm calculating exec. So exec is actually calculating all of these thunks. And so the order of thunks that it's doing is that it knows that to run this function, which calculates the online stat, and then I'm going to merge them all together at the end. And so now that I've executed it, stat is a real thing. It's no longer a thunk. And then I can plot that so I've combined all these things into each different date. So here is, New Year's Eve. We can look at, I don't know, July 4th. And this shows us the distribution of passengers for any given date. And so that is what we've calculated there. All right. So that is all I have in terms of examples and stuff to go over. So if there's any questions here, yeah, throw them in the chat or unmute yourself and go ahead and ask. Oh, gotcha. All right, we have some clarification. Open int is open interest. Gotcha. Thank you for the clarification.
As Josh mentioned, you can type in your questions in the chat or unmute, ask. There's a question, Josh.
Oh yeah, got it. Yeah, is it possible to create streaming time windows? So yes, there is. The only thing is that we can calculate a circular buffer, let's say of integers, and let's say it's 10 long. Oops. Exported that. In OnlineStats base, there is a circular buffer type. Okay, there we go. So say I fit this thing on 1 to 100. You can see that it's only calculating, you know, the last window. So while it doesn't exactly calculate a statistic on a moving window, it helps you at least monitor that moving window pretty easily, and then you can apply whatever function you want to it. If you're calculating like a windowed mean, so something similar to that is an exponentially weighted mean, and different weights are actually something that is built into OnlineStats. So if I give it a weight of exponential weight 0.1, I can fit this on whatever different values, and this gives it an exponentially weighted mean, gives it the kind of the influence of the newest observation is always constant to be 0.1. So an exponentially weighted mean is very similar to a windowed mean. And similarly, you can use an exponential weight with just about any statistic in OnlineStats. So you can emulate windowed statistics using an exponential weight, but windowed stuff is not quite built in. Do any of the OnlineStats? How efficient is Pluto compared to Jupyter? So I'm a huge proponent of Pluto since it came out. The biggest thing is like how reactive it is. So I was so used to like restarting Jupyter notebooks just to get everything to run in order, and you don't need to worry about that with Pluto since it's all reactive. I'm not sure what you mean by terms of efficiency, but if anything, it's less laggy and buggy than my experience with Jupyter. All right, and then on to the next one. So do any of the OnlineStats algorithms work with multidimensional arrays or tensors? There's nothing that is quite built in to like analyze multidimensional arrays. It would be fairly easy to build one in the sense of, right, so if I create some subtype of OnlineStat that is, I don't know, array 5 and so struct. Anyways, well, so okay, pretend I finished writing the struct and I spelled struct correctly. So I could create a new OnlineStat that is a subset or a subtype of OnlineStat of, you know, and this is telling it that the single observation is a 5-dimensional array of integers. So then you could then define your own fit function that whatever updates whatever calculation it is that you're using for this multidimensional array, but nothing that is quite built in at the moment. How easy to support multi-pass data scanning? So I might need clarification on what you mean by data scanning. Oh yeah, okay, so. so I just posted the link to where all the slides are. Data scanning as in selectively used data. Yeah, so one thing that I have been really big on is making wrapper types. Transform. So filter transform is, let's say, it's a wrapper around an online stat that lets you kind of filter the incoming data. So let's say I have a vector of strings that I want to calculate. Will that contain a number? And so I need to parse those things, and I want to calculate a mean. So you can define this as, all right, so my input type is a string. I want to filter that as, let's say I want everything in there. Let's see, not is empty. Say I have some empty strings in there. I then want to Okay, so this is just my own kind of little clever-ish syntax. So this is saying I have an input variable that's a string. I'm going to filter it with it's not empty. And then I want to parse that string as an integer, and then I want to give that to a mean. So I'm going to hit that, and then I can fit that with so here is an array of strings. And so here it's skipping over this middle one because it's empty. And then it's parsing these other strings as integers and providing it to the mean function. So there's a couple of these kind of different wrapper types that you can wrap around any other online stat. So you could wrap around this around, a linear regression for filtering observations or whatever you want. There's a couple other types like that, that's skip missing is one. So I can now fit this object on missing data, and it's just going to skip those. Yeah, hopefully that answers your question there. See, what Julia programming resources have you found most beneficial to writing your package online stats? Oh, so that's a good question. I think for me, it was a lot of trial and error, just because I started using Julia. I think it was 0.3 had just come out when I started using it. And it wasn't for, I don't know, another 2 years or more before 1.0 came out. So I can't remember any kind of like fantastic resources other than the official Julia docs for learning stuff. And then also there's a lot of kind of mentorship in the community of, so Tom Breloff is one of the people that kind of helped me get started with online stats. And there's my PhD advisor, Hua Zhou, was very helpful. There's several other kind of Julia folks that really helped me along. Nothing really written down though that I was able to, follow really well. Yeah, thanks for attending. Yeah, happy to be here and talk about this stuff. I'll hang on for I don't know, another few minutes here, just in case anyone else has something they want to talk about. Oh, and my actual slides, they're not in this repo yet. I'll add them as soon as I hang up here. All right, so I'll answer this one first here. I'm currently developing a package. How do you get feedback from the community on the code? Well, I guess, so for me, I guess I started working with someone who was kind of interested in the same set of problems. And so we were both working on online stats. So this is Tom Breloff, and he was kind of the more mature programmer between the two of us by a wide margin. And so he kind of, kept making, pull requests to OnlineStats, and then he would give very useful feedback. So if you can find someone who is interested in the same thing that you're working on, that's probably the best way to get feedback. Yeah, you could also just like asking for help on Slack or Discourse. I'm sure there might be a few people, depending on what you're working on, that would be interested in taking a look on what you're working on. Okay. All right. Suppose you have a big data set A as input and you don't want them all in memory, and you're computing some analytics for each item from another big data set B. In each of B, you need to selectively use some data from A. How does Julia deal with this situation? I'm not sure I completely follow here, but it's almost like a lazy database join. So if I'm working with one table and I need some information from a separate table, I'm not sure if there's a perfectly clever way to do that. Yeah, so sorry, I don't have a good answer there. Is there a link to the documentation for your packages? Yeah, so where I just linked to, if you click Josh Day, yeah, OnlineStats will be my first pinned package there. And there are the docs there. All right, so there is the OnlineStats docs I just posted in the chat there. Does it do SIMD? You could probably, well, no, so no, it doesn't. I don't know how complicated that would be to actually add, or like if just throwing SIMD on a for loop around your fit function would be enough. I haven't experimented with that enough. Oh, looks like when I left, the stopped running. Bummer. If you think of any questions after we hang up here, feel free to send me an email or find me on the Julia Slack or wherever. Happy to answer more stuff.
We'll be on maybe for a couple of more minutes. In case you have any questions, do send it in.
Have I used OnlineStats with TARDIS APIs? No, I have not. Yeah, so I kind of wrote OnlineStats almost as a, I don't know, a mental exercise, or like a, so my research was into online algorithms for statistics. So I was almost less of solving a problem as I was inventing algorithms for algorithm's sake. Yeah, so actually the data sets that I've actually applied this stuff to is actually pretty small. I think it's really useful for big data sets, but I just haven't really done that. Let's see, acknowledging the clear memory benefit, is it a bit less efficient on the CPU? For example, one thing we lose relative to having all the array in memory is SIMD. Yeah, that's a big thing, right? So if calculating a mean sequentially is a lot, well, I don't know if it's a lot slower, but it's definitely slower. So yeah, you lose out in a little bit of speed. So here is a million things. And if I do fit, yeah, so just using the statistics mean I'd save, I don't know, 5 times the number of time. This is a very noisy estimate, but yeah, so using, if the offline version is available to you, that is probably faster because of things like SIMD. But in the cases where you're working with, truly streaming data, like what's happening on the left side of my screen here, or you can only load your data in batches because you have a gigantic data set, that's where OnlineStats becomes useful.
Great. So shall we call it a day, Josh?
Yeah, sounds good. Yeah.
Yeah.
Thanks everyone for attending.
Yeah. Thank you, everyone. And thank you, Josh.